Well, dear friends, this is a very important rule, Bend's rule, known as Bend's rule, to predict theoretically the structure of various, I mean, molecules, and particularly in a non-equivalent hybridization. Means when there is a non-equivalent hybridization, or molecules in which elements of different electronegativity are involved. So, by using this rule, you can predict the bond angle and correct structure of the molecule. What should be the correct structure and correct population of given structure? So, first, I'm going to give you the formulation of this bent rule and then application. Maximum application you will get for non-equivalent hybrid orbitals. So in case of, I'm giving you the statement in two parts. First part, in case of, in case of hybridization like sp3d, non-equivalent hybridization. The more electronegative, the more electronegative element prefer to attach or overlap with less electronegative hybrid orbital. Hybrid orbital. See, this is very important. I mean, theoretical general observation, you can say less electronegative hybrid orbital, right? More electronegative. See, these are the keywords. More electronegative element. So, if you have elements of different electronegativity, in case of any molecule, like see here PF2Cl3, and in case of non-equivalent hybridization, see non-equivalent hybridization is there. So more electronegative element, see more electronegative element prefer to attach. See, I am not here in hurry, I am going slowly here because this is very important and very helpful for you. So please listen carefully, and all of you should write each and everything in your notebook. So more electronegative element prefer to attach or overlap with less electronegative hybrid orbital, and this is possible in case of non-equivalent hybrid orbital. So in case of sp3d, if we see here, in case of sp3d, in case of sp3d, we have this type of and So these are axial bonds. Two axial bonds are there and three equatorial bonds are there. So which one is more electronegative? Equatorial bonds are more, electronegative, and axial bond. So electronegativity of axial bond is less than the electronegativity of equatorial bond. So the more electronegative element prefer to attach with what? Axial bonds. See, although there is a flexibility in molecule, and this molecule, these axial equatorial bonds are always in pseudo rotation. This in this particular hybridization, this term was introduced, that bonds are in the pseudo rotation. So axial bonds becomes equatorial, equatorial becomes axial. This is mixing taking place at room temperature. But that's why I have told you here that the most prominent structure, I am not denying any structure, any possible structure here. All structures are possible, but the most prominent structure is one. Structure one means if you quantitatively analyze this molecule, then you will find that the population of this structure is maximum, right? Population of this structure is maximum here. So I am not denying that this structure is not possible, this structure is not possible. All the structures are possible, but the population of this is more prominent structure is this. Okay. Now here the more electronegative element, if all have same electronegativity of all the elements have same electronegativity, then there is no problem, right? So see, first I will do some example based on this. After that I will state you the second part of this, right? In the second case, now see, suppose that if you have a molecule like SF4. So in case of SF4, what is the hybridization of sulfur? The hybridization of sulfur hybrid orbitals. Hybrid orbitals is equal to 1 by 2. Number of valence electrons 6. Plus fluorine is monovalent, so 4, 10. So this is equal to 5. And the hybridization is sp3d. So in the sulfur of this molecule, the hybridization is sp3d, right? Now see, how many bond pairs are there? So 5 hybrid orbitals means total 5 electron pairs are there. 5 hybrid orbital means 5 electron pair are in this molecule. In this molecule, right? 4 of them are bond pair, 4 are bond pair, and 1 lone pair, right? Now see, again the situation here, different. How? This is a non-equivalent hybrid orbital. If it is the case of equivalent hybrid orbital, then there is no problem. Then there is no problem. You can put bond pair anywhere, lone pair anywhere. But since it is the case of non-equivalent hybridization and hybrid orbitals, then the situation is different. So put sulfur here, and you have two possibilities here in this case. One possibility is that lone pair is here at one of the axial position and all other are bond pair. Similarly, other possibility is that see, there are two structures possible here, right? Structure 1 and structure 2. Now tell me which structure is prominent here, or which structure is more contributing, you can say, at room temperature. So apply the Bend's rule, right? Here one is lone pair and four bond pair, and bond pair constitute fluorine. So now tell me which is more electronegative. Lone pair is more electronegative or fluorine is more electronegative. So obviously any atom is more electronegative than lone pair, because in case of electronegativity the nucleus will attract the bond pair of electrons. So here in lone pair there is no nucleus. So the fluorine is more electronegative. So as per the Bend's rule, see, more electronegative element prefer to attach overlap with the less electronegative. Electronegativity of axial bond is less, so fluorine will occupy the axial position, not the lone pair. So you can say here, you can put a note here, in case of sp3d, the lone pair or pairs always occupy equatorial position. This is always true. This is always true. There is no problem. This is always true. So the most prominent structure is structure number 2 for this molecule. So structure 2 is the prominent structure. Right? The prominent structure. Although both structures are possible and dynamic interconversion is always taking place, but this is a more prominent structure, right? Now see, and now what you will tell about the geometry of this molecule. So the geometry of this molecule is TBP, trigonal bipyramidal. But what is the shape of this molecule? The shape is, now see, which shape you are going to explain, number 1 or number 2? You have to explain the shape for number 2. So if you see here, this is you can say the base, this is base, and this is what in park all of you see seesaw. So this is basically seesaw shape, you can see, right? So shape is seesaw and geometry is TBP. Geometry, strictly you will see the hybridization, but shape is actual bond orientation of bond pairs, not lone pairs, right? So exclude lone pairs, then whatever is the left, that is basically shape, right? Now see another molecule ClF3. So now you can calculate and you will find that, okay, what is the hybridization here in case of CLF3? The hybridization is sp3d. Now you can calculate. Now you have, all of you are equipped to calculate. Now see how many bond pair? Bond pairs are 3 and lone pairs are 2, right? So bond pair is 3, lone pair is 2, and now it is clear that in case of sp3d, lone pair will occupy equatorial position. So put here Cl, draw the normal structure, and put lone pairs at equatorial position. Since all three equatorial positions are equivalent, so you can put anywhere, and F, F, and F. Now see, what is geometry here? The geometry is TBP, trigonal bipyramidal, and what is shape here? The shape is what? T shape, horizontal T shape, right? So on the basis of bent rule, you can very easily, identify the correct structure of any molecule in case of sp3d hybridization, because this is a non-equivalent hybridization. In case of others, when all the hybrid orbitals are equivalent, then you can put lone pair anywhere, bond pair anywhere. Now see another molecule, I3 minus, right? So in I3 minus, you have central atom I. So number of hybrid orbitals is equal to 1 by 2 valence electrons in the 7 and 2 monovalent iodine plus 2 and 1 negative charge, so plus 1. So you will get 5 hybrid orbitals, in which the bond pairs are 2 and lone pair 3, right? So again you have to use Bend's rule. So put iodine here, 1 iodine. You have 3 lone pair and 2 bond pair. Now tell me where 2 bond pair will lie. Bond pair will lie at axial position and 3 lone pairs will lie at equatorial position, like this. And 1 negative charge is there. Negative charge, like this, right? So what is the geometry of this molecule? The geometry is TBP. What is the shape here? The shape is linear, right? So by considering only hybridization, you cannot predict the actual shape of the molecule. What is the actual shape, right? Geometry you can say, geometry is okay. So this is the what application of this Bend's rule. Some more application, more example I should explain here. Suppose that if you have XeO2F2, right? So again, number of hybrid orbitals. So central atom is xenon. So this is 1 by 2. Number of valence electrons in xenon is equal to 8. Oxygen is bivalent, so its contribution is 0, plus fluorine is monovalent, so its contribution is 2. So you will get 5 hybrid orbital, and this is sp3d hybridization. sp3d hybridization, right? So now see sp3 hybridization. Now we have I mean 2 and 2, 4 bond pair and 1 lone pair. So bond pair means number of atoms which overlap with the hybrid orbital of genome. So see 2 fluorine and 2 of oxygen. So bond pair 4, and total 5 hybrid orbitals means 5 electron pair. So lone pair 1. So as per this Bend's rule, lone pair will go here. See, lone pair oxygen and fluorine. Which one is the most electronegative? Fluorine. So put the fluorine axial, and after that, whatever is left, that put you on the equatorial. So see, XE. These are equatorial bonds, and this is axial bond. So first you have to place fluorine at the axial. After that, 1 lone pair, and then oxygen. And all of you are knowing that if oxygen is there, so this will form a multiple bond, pi bond, like this, right? So this is the structure. So again, now see, if you do not know that where to put lone pair, where to put oxygen, where to put fluorine, so you can make a different structure for this. And all structures are not the correct structure for this molecule. So geometry is TBP and shape is seesaw. Right? So in this way you can explain the structure of these molecules. See, still some more things are required here to do, but that you should do in the next phase. That this pi bond is formed between which orbital, which type of pi bond is this? P pi bond is there, or P pi D pi bond is there. So you have to find out all these things. This is also the part of what structure. But here I'm going to focus only this hybridization, geometry, and shape, right? So this is the first part of this Bend's rule, first case. Now come to the second case, in which hybridization is equivalent, but after hybridization, when overlapping overlapping takes place. So if different electronegativity atoms are involved, then also there is a deformation and there is a change in the bond angle, change in the bond length. All these things can be happen. So now see second case, Bend's rule part 2, you can say. In case of equivalent hybrid orbital, in case of equivalent hybridization or equivalent hybrid orbitals, hybrid orbitals, if elements of different elements of different electronegativity present as present in the molecule the bond angle bond length can be explained by using Bend's law. Bend's rule. Bend's right. Now see. So suppose that if we have CH2 F2. So in case of this, the carbon is sp3 hybridized, and you know this all I mean 4 sp3 hybrid orbitals, they have ideally I mean all are equivalent with respect to their shape, size, orientation, and S and P character. In all these orbitals, it is equal. It is equal, right? But when this, hydrogen and fluorine, they will overlap. So what will happen? See, two hydrogen atom, let they overlap with these two, and two fluorine atoms orbitals, they will overlap. Let's here right. So like this there is overlapping. So post overlapping there is changes. Since fluorine is more electronegative than hydrogen, so what will happen, the orbital, see this was sp3 in which p character is 75%. So the fluorine which attached with this sp3, this will increases the p character here. So once the p character increase, the size will increase, size increase, electronegativity decrease. So you can say indirectly that the orbital to which fluorine atom overlaps, that is less electronegative. That is less electronegative. So it means now that in CH2F2, all four bonds are not identical. Now this carbon fluorine bond, the hybrid orbital has more p character, and you know with increase in p character bond angle decreases. So with increase in p character bond angle decreases, right? So FCF bond angle FCF bond angle is less than HCH bond angle. Clear? So this is also, you can say that Bend's rule we can use in those cases as well where elements of different electronegativity are involved, right? So now you can say that here in this two carbon fluorine bond the p character increases. So obviously in these two the s character increases. I mean p character decreases because overall s and p character, that is the conserve overall, right? So if it is increases, then definitely this will be withdrawn from this bond. So this bond becomes shortened. These bonds are become shortened, means if you compare with CH4, so this will be shortened and this will be enlarged, means its length is increases, right? So this is the, I mean this you can explain on the basis of what this bends. Okay, hopefully it is clear to all of you. It's very useful. Now suppose that it is given to you that CH2X2 is given, and it is asked that see if X is equal to F Cl Br. So what should be the X C X bond angle, right? So if X is equal to F, if X is equal to Cl, so F is the most electronegative. F is the most electronegative. So here the bond angle is smallest, then Cl, then Br, then I. So this you can arrange in this manner. Clear? Any doubt? But here I want to put a note that in case of such I mean compounds, if you compare this F C F and Cl CCl. So the normal bond angle is 109 degree 28 minute, right? This is the normal bond angle for tetrahedra, or you can say sp3. Here it is less than the normal bond angle, but this is more than the normal bond angle. This is the normal bond angle, right? Means this FCF bond angle is less than what? 109 degree 28 minute. What it is expected. But this Cl, CL bond angle, that is, greater than normal. Okay, that is greater, but greater than fluorine as well, no problem. And that for bromine, it is greater than this chlorine and than this, right? So see here this fluorine, and if you compare with the CH4 hydrogen, you can say HCH bond angle. So this will fluorine will go down, but chlorine will go up. means chlorine, this is I think 111 degree and this is 108 degree, right? It is close to 108 and this is 111. So the important thing is that despite increasing the electronegativity, their size also increases. So if the size, volume of atom if increases, so bond angle accordingly that will increase, right? Because in space it requires more volume, right? So that's why this is increases than the normal value. So normal is 109 degree 28 minute. Don't say that electronegativity here is more than hydrogen for everybody, then all bond angle will less than 109 degree 28 minute. No, 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 not like that. This is, I mean, in case of fluorine, it is a small in size. This is second period element, then it is okay. It is lesser than the normal bond angle, but for others, it is greater than normal bond angle. Okay, so hopefully all of you are clear in this regard. Now you can use this to explain various questions based on this concept. So suppose that, see, one more point we can add here regarding bond angle, that if hybridization is same, hybridization is same, number of lone pairs, lone pair or lone pairs same, then with increase in and one more thing, I mean atoms, surrounding atoms are same. Surrounding atoms are same. Then with increase in electronegativity of central atom, bond angle increases, right? Bond angle increases. So suppose that if you have two examples, NCl3 and PCl3, right? NCl3, PCl3. Now see, one lone pair here, one lone pair here. Hybridization is same. See, 538, 538. So sp3 and sp3. Okay. So hybridization is same, lone pair is same, surrounding atoms are same. Then electronegativity of nitrogen. See, the electronegativity of nitrogen is more than the electronegativity of phosphorus. So in this situation, what will happen? The NCl bond angle is more than the Cl-P-Cl bond angle, right? So this also you can add to your I mean important points, that if other things are same, Then with increase in electronegativity of central atom, the bond angle what increases. So with increase in electronegativity of central atom, bond angle what increases. This is also an important point. Now see, suppose that it is given OF2 and OCl2, right? So in this case, what should let the bond angle is X and this bond angle is Y. Now, what should be the correct answer here? X is greater than Y or X is less than Y? So which one is correct? Electronegativity is more, other things are same. So in this situation, the bond angle decreases, right? So the fluorine will overlap to that orbital which has more p character, means after overlapping this will increase the p character. So in this situation the bond angle here in OF2 it is what less than OCl2, and if you want to the value, so you can see 102 and 111. This is 102 and this is Y is 111, right? So in this way you can use the Bend's rule and theoretically you can predict the bond angle as well, right? See what Drago's rule, actually this is not basically rule, this is you can say observation, but okay, since it was observed by Drago, so you can say Drago's rule that in P block, in P block in P block the elements of third period and higher, or you can say fourth, fifth period. So in P block the elements like phosphorus, arsenic, antimony, and sulfur, selenium, tellurium, right? So in the P block, the elements like phosphorus, arsenic, antimony, and sulfur, selenium, tellurium, when combines with hydrogen, particularly with hydrogen, right? So hydrogen then almost pure p atomic orbitals are involved in bonding, means there is no hybridization. So suppose that if you see the bond angle in case of NH3, PH3, ASH3 and SBH3 and BIH3 also no. So if you see the NH bond angle here 107.5, in PS3 I think it is 93. this is 93, this is 92, and this is 91. Now tell me, what is the bond angle between px, py, pz? 90 degree. So, and here you are getting 93 degree. So what you can say, is there any hybridization in phosphorus? Is there any hybridization in arsenic? Is there any hybridization in antimony? The answer is no, because the bond angle is close to the pure bond angle of pure p atomic orbital, right? And in case of ammonia, there is a change in the bond angle, it is close to 109. So this is close to N09, so we can say that okay, in ammonia there is hybridization sp3, but there is no hybridization in these molecules. Similarly, if you see H2O, H2S, H2Se, H2TE. So here 104.5, and in H2S it is I do not have, but here all are close to 90 degree, right? So in these cases there is no hybridization, but here it is sp3, right? So this is also an observation that if you move down the group, the bond angle decreases in case of what, hydrides. Now see, the thermal stability of these hydrides also decreases down the group. Why? Because you know the hybrid orbital, here some hybridization, and hybrid orbitals always form a stronger bond. So as you move from top to bottom, the thermal stability of these hydrides decreases. Thermal stability if decreases, then reducing power increases, because you know if they provide hydrogen, so obviously hydrogen is a reducing agent, so the reducing character increases. So in this way you can explain all these properties depending on the bonding. So bonding is the important part or important concept of chemistry, right? So this is Drago's observation basically. So see, now I will discuss this some more points to explain explain this observation. After overlapping how this p character and bond angle, all these are changing, so I will discuss that also, right? So see, now if you want, you can write this H2S. In H2S 92 degree, right? H2SE 91 degree, and H2TE 89.5 degree. 89.5 degree, right? So see, so in the next lecture I will discuss more about this bond angle and other factors of this, and after that I will start Vsepr model, right? So I think three or four lectures more will require to complete this. So hopefully in the next week we will complete.